Hello everyone, I am Professor Anishwara and I welcome you all in our next video lecture. In this video lecture, we will study about dispersion coefficient for three-phase induction motor. In case of three-phase induction motor, dispersion coefficient is very significant because some of the performance parameters like power factor, like overload capacity of the machine, like maximum output, that all depend on dispersion coefficient. So dispersion coefficient is very important. Let us start with definition of the dispersion coefficient. How we can define dispersion coefficient? Dispersion coefficient is nothing but a ratio of magnetizing current to ideal short circuit current. So magnetizing current we know that power factor of the machine, that is largely dependent on the magnetizing current, and dispersion coefficient is directly proportional to the magnetizing current. So there is direct relationship between magnetizing current and power factor. So if magnetizing current increase, then we know that power factor always decrease. And same way, we have ideal short circuit current. In case of ideal short circuit current, dispersion coefficient is inversely proportional to the ideal short circuit current. Now, ideal short circuit current, that is stator voltage divided by leakage reactance, where XS, that is total leakage reactance, referred to the stator. Now here we say ideal short circuit current. So what exactly we mean by ideal short circuit current? So if resistance of the winding is neglected, then short circuit current is purely restricted by system's leakage reactance, and then we call it ideal short circuit current. So leakage reactance and ideal short circuit current both are inversely proportional. So if ideal short circuit current is higher, or in other way, if leakage reactance is less, then how it affects the power factor? So we have a relationship between ideal short circuit current and the leakage reactance. So if ideal short circuit current increase, then there must be a decrease in leakage reactance, or it is a vice versa condition. If leakage reactance is less or it is decreasing, then our ideal short circuit current will increase. And dispersion coefficient is inversely proportional to the ideal short circuit current. So if ideal short circuit current is increasing, definitely power factor will also increase. So both the quantities are very important. Magnetizing current, ratio of magnetizing current to ideal short circuit current. So dispersion coefficient, if we substitute value of ideal short circuit current, that is stator voltage divided by leakage reactance, total leakage reactance referred to the stator. So ultimately, dispersion coefficient is directly proportional to leakage reactance as well as magnetizing current, because our stator voltage normally remain constant. For any given stator voltage, dispersion coefficient is directly proportional to these two quantities. So if dispersion coefficient increase, power factor must be decreasing. So high value of dispersion coefficient result in poor power factor, reduced overload capacity, and reduced output. So if we see the graphical representation of our circle diagram, then let us see one by one, and from the graphical representation how we can derive our dispersion coefficient. So on the x-axis we are taking current axis, and at y-axis we are taking our voltage axis. We take no load current or magnetizing current, and that is OA. OA, that is our magnetizing current. We are taking OB, that is our ideal short circuit current. We are taking both the current on x-axis because we are taking ideal short circuit current. So we are avoiding or we are neglecting resistance. And with the diameter AB, if we take diameter and if we take draw our circle diagram, then it will be like this. Diameter of the circle diagram purely depend on the leakage reactance. So if leakage reactance is less, diameter will be more, and if diameter is more, then we have maximum possible output power. So as we discussed earlier, our dispersion coefficient, that is a ratio of magnetizing current to ideal short circuit current. From the graphical view, we can see that OA, that is our magnetizing current, and OB, that is our ideal short circuit current, show ratio of OA to OB, that is dispersion coefficient. Now we have two conditions based on dispersion coefficient. First condition is a maximum power factor, and second condition, that is all load capacity. These two parameters are very affected by the dispersion coefficient. So in case of how dispersion coefficient affects or on our maximum power factor, this will see. So from the same circle diagram, if we need maximum power factor, so angle of the current with voltage axis should be minimum. So if we draw full load current line which is tangent to the circle diagram, that is line OD. OD is our full load current line, and that is tangent to the circle diagram. So if we take a center C, and if we draw one line DC which is perpendicular to OD, it is making an angle 90 degree with OD. So angle which current is making with voltage axis, that is angle VOD, that is our 5 minimum. This is our angle which decide the power factor. From the trigonometry, we can see that angle DCO, that is also 5 minimum. So angle DCO, that is also 5 minimum. So with this reference, if we derive for maximum power factor, then let us see. So maximum power factor, that is cosine of angle 5 minimum. So if angle is minimum, we know that cosine will be maximum, and we have maximum power factor. So we take our circle diagram for reference, so it can be easier to understand different parameters. So cos 5 minimum, that is a sine COD, sine of COD. So that angle is equal to DC divided by OC. So DC divided by OC, that is our sine of COD. So that is exactly equal to DC, that is radius of the circle diagram. So it is AB is our diameter and AB divided by 2, that is the radius. So DC we can substitute AB by 2, and OC, O and C. So OC can be OB minus BC, and BC is again radius. So radius is AB by 2. So ultimately we have this equation. So that can be derived further. If we take 2 as a common factor, then it becomes AB divided by 2OB minus AB. If we further simplify this equation, then it is AB divided by 2OB minus, we have substituted value of AB. AB is nothing but OB minus OA. So with this reference, maximum power factor, that is OB minus OA and divided by OB plus OA. So if we divide both the side with OB, then it becomes 1 minus OA divided by OB divided by 1 plus OA divided by OB. Dispersion coefficient, we know that it is OA divided by OB. OA, that is our no load current, magnetizing current, and OB is ideal short circuit current. So ultimately we have maximum power factor, that is 1 minus dispersion coefficient divided by 1 plus dispersion coefficient. So we have obtained this equation for maximum power factor. So let us substitute some values. For example, if we take dispersion coefficient as 0.05, then maximum power factor is equal to 0.905. And if we take dispersion coefficient 0.1, so we have doubled our value of dispersion coefficient from 0.05 to 0.1. Then our power factor maximum is equal to 0.818. See, here we can see the difference, 0.90 to 0.81. So there is a significant decrement in maximum power factor when we have doubled our dispersion coefficient. So it can be concluded that there is a large decrease in maximum power factor when dispersion coefficient increase. Okay, same way, if we see the effect of dispersion coefficient on overload capacity, then with the same circle diagram we can further derive overload capacity. So let us draw output line with respect to our full load current. Our full load current line is OD, and if we draw a line that is DE, which is perpendicular to OB, then it indicates our maximum power with respect to our full load current or full load output power. Same way, if we draw the maximum possible output power, then we can draw one line which is again perpendicular from center C. AB is a diameter of the circle diagram and C is the center of the circle diagram. From the circle diagram, from the center of C, if we draw a perpendicular line to AB, then it indicates maximum possible output power, and then it is FC. So if we now need overload capacity of particular machine, then it is a ratio of maximum power output to output at full load. From the circle diagram we can see that F and C, that is maximum output power, and D and E, that is output with respect to full load. So overload capacity is nothing but a ratio of FC to DE, that is a maximum output power and output at full load. So again, overload capacity, as we have seen that it is a ratio of FC to DE. We take this circle diagram as a reference, so we can further derive the equation for overload capacity. So FC, that is nothing but a radius of the circle diagram. So FC can be taken as equal to the AC. AC is also nothing but a radius of the circle diagram. So FC can be taken as AC and DE. So DE can be taken as a DC and angle sine of this angle. So it can be DC sine phi minimum. Phi minimum is our angle and sine of this angle, that is a DE line. So DC is also a radius of the circle diagram. So AC and DC can be compensated each other. Then ultimately overload capacity is equal to 1 upon sine phi minimum. If we further simplify this equation, then it becomes 1 divided by under root 1 minus cos square of phi minimum. Further simplification give this equation, and if we take this equation as a base, then ultimately for overload capacity we get this equation 1 plus dispersion coefficient. In terms of dispersion coefficient, we are deriving our equation for overload capacity. So it is a 1 plus dispersion coefficient divided by 2 under root dispersion coefficient. So this equation is for overload capacity. Now suppose we again take similar values which we had taken earlier to calculate maximum power factor. Suppose we take a dispersion coefficient as 0.05, then overload capacity will be 2.34 times. So if we now double the value of dispersion coefficient, that is from 0.05 to 0.1, then overload capacity will decrease, almost decreasing to half, that is 1.58. So it can be concluded that there is a sharp decrease in overload capacity when dispersion coefficient increase. So this way we have seen that dispersion coefficient is very significant. Dispersion coefficient affects our overload capacity as well as power factor. When dispersion coefficient increase, power factor decrease as well as overload capacity also decrease, and dispersion coefficient is directly proportional to two quantities. One quantity is magnetizing current and another quantity, that is our total leakage reactance. So this way, while designing our three-phase induction motor, we have to take care regarding our dispersion coefficient, because performance parameters largely depends on this parameter. So I must stop here. I think we have discussed dispersion coefficient, significance of dispersion coefficient at large. In next lecture, we'll discuss some more performance parameters like calculation of no load current, calculation of short circuit current, So thank you very much. Keep watching my video. Thank you very much.